You should have some notes out because we're going to notes it up right now. I bought this cup and I guess it has Diego on it. That's what they told me about yesterday. Is that true? Is that who that is? I'm not familiar with these characters yet, but I'm sure that I will learn very soon. But yeah, I just thought it was cute. But anyway, okay. I'm going to throw some water in here just because it makes it more fun. All right, and then what I'd like you to do is to draw a free body diagram of this, we'll call the cup and the water a system. Okay, so the cup and the water are a system, and instead of drawing 3 strings and having to deal with a z-axis, which doesn't seem like a super whole lot of fun, we can assume that all of these strings are pulling from one place. Does that make sense? And what I'd like you to do right now is to draw a free body diagram of the cup. Okay, when I say cup, I really mean the cup and water together. Okay, so here's the system, here's the situation. Nothing magical is happening, friends, right? I did Diego cup from Dixie, right? That was the brand. And then it's a string on the top, okay? So go ahead and draw a free body diagram of that system for me and for yourself. All right. Do you feel like you've had sufficient time to draw that free body diagram? It's not a big scary thing. Okay. All right. Michelle, are you feeling brave today? You can say no.
No.
Oh, okay. Hey, Brittany, are you feeling brave today?
Sure.
Sweet. Come on up here. Yesterday, the person that I picked on happened to have these like big Spider-Man glasses on. Do you have Spider-Man glasses today?
No.
No? Okay, well, that's okay. What's that?
They're my teacher's shoes.
Oh, they're more teachery than my shoes. So good. I'm glad you're here. Lay down. All right. Are you comfy?
Sure.
Okay. Do you want goggles?
I'm fine.
All right. So now we're going to just make life a little more fun. Yes? All right. So I put some water in here. We know that, right? Okay. You ready? You ready, Alex? Excited about this? See, I didn't put her here because, who knows what would happen. I almost picked on you, but I was like, no. Okay, here we
It
go.
would probably fly across the stage.
Right? Like, whoa! Something
It
terrible.
would hit Addison somehow.
Somehow. He's in wherever. Sevilla. And
Right.
somehow you, okay, you ready? Okay, here we go. How you doing? Good? All right. Are you getting wet?
No.
Okay, that's good. Because if you were, then there would be a problem. All right. So that's fun. That's exciting. Yay. All right. Good job. Okay. Everybody excited about that? That was pretty good. Do you want to drink some water? Okay. I don't want to, let you down. Okay. You can go sit down. I'm going to dump that back in here just so that when I hold this up here to ask you to draw another free body diagram, kind of maybe next to it or a little bit below, somewhere on your notes, I want you to draw a free body diagram of the cup. So when it was going around in a circle, at the point where it was up here. Cup and water system, I want you to draw a free body diagram of the cup at that point. Oh, she's making me think on the day before spring break. It's not fair. Yeah. So the cup is sitting up here. The water's up in the cup, obviously, since Brittany did not get wet. Is that true? She did not get wet. That's good. That's good. Okay. So go ahead and draw that free body diagram. Okay, let me see those boards.
Yeah.
Okay.
Oh no.
All I wanted was the first one, but I want you to label them like you're supposed to label a free body diagram, so work on that again. Okay. And I just want the first one, so I don't know which one's the first one, so only draw the first one. Only the first one, only the first one, so I don't want the second one. Put the second one away. Erase it. That's what we have the beautiful whiteboards for, because then we can erase things. So let's start with just the first one. String on cup, earth on cup. String on cup, earth on cup. String on cup, earth on cup. You said carbling on cup. Woo! But yeah, I mean, it's the same kind of deal, right? I mean, if you call the string part of that, that's totally fine. You write so little. What does it say?
String on cup, earth on cup.
String on cup, earth on cup. Okay, so the string's going up. The earth is going down or pulling down. Force of the earth on the cup. Force of the string on the cup. How do those two forces compare?
They're the same.
How do you know?
Not moving.
Wrong. It's not what?
Accelerating.
It's not accelerating, right? And I've been trying to indoctrinate you. I've been working on this for a lot of months, right? Yeah. It's not that it's not moving. It's the fundamentally interesting thing here is that if we add up the net forces, so if you haven't written this down on your paper, you might want to do this too. We're just going to write this down. So this is the tension force, right? And this is a gravitational force. So we can say Fg plus Ft we know equals ma, but a is 0. So that means that Fg and Ft have to be equal. Is that okay? All right. Now I want you to have the conversation about the top. So if you already had that conversation, just draw that picture. And if you haven't had the conversation yet, then have the conversation quick. Go ahead and draw the forces that are acting on the cup water system, at the top of the story. All right, let me see your pictures. You have two pictures. Oh, that's the first picture. Oh, okay. See, you're just
Like
confusing me.
I know, because it's not accelerating. But
Okay. Okay. What do we know for sure is acting? Michael, what's one thing that we know for sure is acting?
Force of gravity.
Force of gravity. Why do you know that that's acting?
It's always active.
Because, right? If you're near the surface of the earth and you have something with mass, then yeah, absolutely. Right? So you've got the force of gravity, the force of the earth on the cup. Jenny, Ty, what else do you know for sure?
The string on the cup is acting on the cup
And where's that one going?
down
Why?
because the string is going down.
So it has to follow the string, right?
Yeah.
Sure. Okay. Now, that's what a lot of the pictures on the boards look like. Raise your hand for me if your picture did not look like this when you drew it on your paper, though. Did it look like this? Not on your paper? Did you all have this exact thing drawn? Yeah? 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 Peter, why not?
It started from us and it had velocity going left and right in the x direction.
Mm-hmm.
And so I assumed there had to be a force there, but it may not have been at that point.
So where did you want a force to be acting? Which way?
I had it going left, but it depends on the point of view of the person.
So, but to the left or to the right?
Yes.
You wanted something going horizontally. So something, let's just say this way? Some sort of something going that way? Did you have a name for it?
Not really, no.
Okay.
I just didn't know.
Just that there was something.
Yeah.
Okay. Okay. Keegan, is that the extra one that you had?
no, I had it going in the opposite direction because it's not
Like in the opposite horizontal direction?
no, opposite vertical direction. Because
So you had a force going like this.
yeah, because it's not accelerating in either. It's not accelerating in either of those directions.
Okay.
So that means it's got to have another, like a force that cancels out with gravity and string, doesn't it?
Well, I don't know. I mean, that's the question, right?
I had that too, but I don't know what to call it.
Yeah,
Okay.
that.
Who else had that besides anybody else? Yeah? I will tell you that 99% of the people in 99% of the classes have a force up there too. Seems like there should be, right? Because the water's not doing what?
Falling out.
So
Not falling out. If the water's not falling out, then it seems like there's got to be something pulling it up to prevent it from being pushed down. But nobody at this table told me that you had a force going up. Why not? You just had these two. Is that right?
Yeah.
Does that bother you?
It bothers me.
Can you tell me why it bothers you?
feel like there has to be something else. Like
Okay.
going up because there's no like depth,
Okay. So I'm just probing a little bit more here. So when you drew it on your picture, you only had these two
Yeah.
because you knew that they existed,
Yeah.
but you kind of wanted to put something else here,
Sort of.
but you just didn't have time or wasn't sure what it was or something like that.
Yeah.
Okay. Okay.
No,
Peterson.
I know there's gonna be some catch, but what I feel like is that there's only one lid. So like, if there wasn't a lid on the top part or the bottom of the cup, I guess, like if there's no lid, it's just a hollow cylinder, then the water would go at the top. But because there is a lid, the lid or the bottom, whichever one we would call it, is pushing down the water, so that there's only force, like net force has to go down. Because like, if net force was 0 and you did that, the water would fly out the top. But because it doesn't,
Wait, hold on. If the net force is 0, it's going to fly out the top?
no, if there was no lid.
No,
Yeah.
no. In order for the net force to be 0, there has to be a lid, is what he's trying to say.
Is that what you're saying?
If it was just a hollow cylinder that you had water in that was somehow staying in, even though there was no thing, and you started spinning it at the top or anywhere, water would fly out. Because it doesn't, that means that the bottom of the cup is pushing back on the water, or like pushing towards the...
In on the water.
Yeah. So,
And why is it falling up on the bottom?
because the cup is constantly pushing down the water, so like you can't catch up to it fast. Like
I'm not convinced.
the cup is pushing the water always.
Amanda's not convinced.
Because if it wasn't pushing the water would come up back.
Wendy?
So the string is like always turning it. So like it's moving this way and then the string moves it this way.
Uh-huh.
So then it like kind of keeps it in and then it's like moving up. The water's moving up and then you turn it this way. That's
Which
why-
is going a little bit against what Michael just said. Like, I think it's kind of there, but I think, okay. Come meet me over on the floor over here.
Everyone?
All of you. Not. Then we're going to come back and put this all into context with our water. But let's come here and actually, why don't you go ahead real quick for me and draw yourself a circle. And let's put the yo-yo on the circle. Right there. Just so that we can talk about all of that stuff that we just went through, but just to make sure that we understand. So that circle is really just the trajectory. And the yo-yo is going around like this. We know that there's a gravitational force pushing in, right, onto the floor, and there's a normal force pushing out. We get that. But as this thing is going around, really there's only one other force acting, right? That being the force of the string pulling which way? In. Is that making sense? Okay. We've agreed that this object is accelerating. We know that it's accelerating because there's a change in velocity over time, and I'm just going to write down what we had there so that you got it in your notes too, that the velocity means that we're either going to speed up, slow down, or the most important one for today is change direction. Okay. The topic of the day is uniform circular motion. So if we work backwards in that phrase, motion is pretty straightforward, right? Something moving. It's moving in a circle, so that means that we know the trajectory of it, right? The uniform part is the really important piece here. Uniform means that it is at a constant speed. Okay. We know that it's accelerating because it is changing direction. Right now, would you please draw the velocity vector that describes, again, if Alex got her little magic scissors out and cut that string, where would that yo-yo go? Where would it go? Go ahead and draw that velocity vector on your picture. Check it with your neighbors to make sure they agree with you. And And let's see. Lindy, if you were going to describe where that velocity vector goes, what would you say?
Tangent to the circle.
Tangent to the circle, right? So it's going to be perpendicular to the radius, like so. Is that okay with everybody? Okay. Now, at some time later, does it make sense that the yo-yo is going to be somewhere else? So I'm just going to put it over here somewhere else. The exact point doesn't really matter. I'm just kind of trying to get a sense of what's going to happen. And go ahead and draw that second velocity vector. It's also going to be tangent to the circle, right? So it's going to be like this. I'm going to call that V final and this one V initial, just so that I can differentiate between the two of them. I hope that I've convinced you that we are accelerating. The question is, what direction are we accelerating? Oh, like, how do you know that? I don't know. Well, we know that if we look at this equation specifically. To find out the direction of the acceleration, does time have a direction? No. So really we just need to find the direction of the change in velocity. Okay, so let's find the direction of the change in velocity. The change in velocity literally means final velocity minus initial velocity, right? And instead of saying minus, we could also say plus a negative. So let's do that. So we're going to say this is V final plus negative V initial. What does a negative vector mean? Going in the opposite direction, right? Negative 3 is exactly the same distance from 0 as positive 3 is. It's just in the opposite direction. So we haven't done vector addition for ages, but let's try it out. So V final minus V initial. So I'm going to pick up this velocity vector. I'm just going to set it down here just so that I have it to play with. So there's my final velocity vector. I'm going to draw it in green. So it's something like that. And like I said, it's been a while since we've done this. But if we're going to add vectors, you always set them up so that they're aligned what? Do you remember? Head to tail, tail to head, right? So I'm going to put the tail of the second one right at the head of the head of the first one. So if this is VI, I'm going to take that VI and I want negative. So I'm just going to put the arrow on the other side and then move it down here. How does the length of how do the length of those vectors compare? They're the same. Why?
Because they're equal as if uniform circular motion, so it's uniform force.
Not uniform force. That's not what you meant.
Uniform speed.
Yeah, uniform speed. Okay? So it's going to look something like that. And so then if we're going to find the resultant, whoa. I just really want it to be cool. Yes, it should be VI. Thank you for catching that. And it should actually be negative VI. My computer has been really cranky. I think it's just ready for spring break. There we go. And that resultant vector is going to go something like that. Delta V. And if I pick that up, I pick that vector up, and because it's a change of velocity over a little time, I'm just going to put it in the middle. Where does it point? Down. Does that make sense? So the change in velocity vector, which is also the same direction as the acceleration vector, here is pointing down. Is that okay? Is it always going to point down? Let's try one more just to make sure that we're really seeing it. So go ahead and put 2 more yo-yo spots. Maybe we'll call them A and B. Just somewhere else on your picture. And do the same process again. So find the initial and final velocity vectors, subtract them, and find out where delta V points. You can talk to your partners about this as you go, but go through that process real quick. So there's VA, or V initial. And there's VB or V final. So V final minus, oops, let's see, 2, V final, up like that. V initial is like this, so it's going back like that. Oops, that's not long enough. Ah, there we go. Where does it point?
Towards the center.
Towards the center. Okay. Yeah.
Does it split the difference between VA and VB?
Well, okay, so here's the deal, is that I'm just looking right in the middle. So this is really actually a calculus question, right? Because this is really just a derivative. And so really you're just making your spaces as small as possible so that it's actually talking about right at the center.
Okay.
Yeah, does that make sense?
Yep.
Yeah. But for our purposes, because I can't draw two yo-yos that are like infinitesimally close to each other but still have some space in between, it's just easy enough to draw it like that. Yeah. So this is a non-trivial deal, and this non-trivial deal even has a name. This kind of acceleration, because we could do this over and over and over, and those arrows would keep pointing towards the center. So whenever you have uniform circular motion, this acceleration that always points to the center, it has a name. Does anybody know the name of it? Does anybody know this name? It's a pretty fancy name. Yeah. Centripetal acceleration is the kind of acceleration that you will always have in uniform circular motion. Any object undergoing uniform circular motion, okay, will experience what we call A sub C, or centripetal acceleration. The word centripetal, I mean, if we can play the word within a word kind of game. Centra means center or middle. Pedal means seeking. So literally, this is a center-seeking acceleration. It's always going to point towards the center. Is that okay? Center-seeking acceleration. So we know the direction of it. It will always be towards the middle, okay? There is an equation for it, and I'm not going to go through the derivation for it. It's not really that hard, but I just would rather do some problems with this, so I'm just going to go ahead and tell you what it is. The centripetal acceleration, the magnitude of it, is dependent on how fast it's going, v squared, and also the radius of the circle. So that's the magnitude, and it will always point radially inward. Okay. That is centripetal acceleration. Life is okay so far? If it's accelerating, you know from Newton's first and second law that there must be a force, right? That's causing that centripetal acceleration, okay? So anytime we have uniform circular motion, we know that there must be a net force acting. And what direction will that net force act in? Where will it point?
Toward the center.
Toward the center. Right? Because F equals ma, doesn't it? F net equals ma. And those are vectors. Well, the m isn't, which means that wherever the a points, the f has to point. So if we've got centripetal acceleration, which we do every time we have uniform circular motion, that means that the net force has to point in. And now if we take that and we look way back up here, Where is the net force pointing in this picture? If we just take the green ones, it's toward the center. A lot of times people want to put this force up here, this question mark force, but there really is no force up there. Sometimes people want to put a force here, but there really is no force there. You can reason this through in a couple of ways. One way you can say, well, a force has to be either one of the four fundamental things, gravity, electromagnetism, strong and weak. It's not one of those three because we don't know anything about them, right? So it's either got to be gravity or it's got to be like a mechanical contact force, which means something is touching it. There's nothing else touching the cup except the string. So that's got to be it. Okay. But my question for you is, why doesn't the water fall out? There's a net force pulling which way?
Toward the center.
Down, towards the center, right? There's an acceleration pulling which way? Toward the center. Down in this case, right? If I take this glass of water, I don't know if Brittany wants, well, I could do it over your head, and I just go like this, right? Where's the water going to go? Down onto Brittany's head, right? But when I've got it in this fancy cup, and there's nothing magical, I mean, it's just a Diego cup from Hy-Vee, friends, okay? There's nothing magical here. I pour it in here and I swing it around. It didn't fall on your head, did it?
Because the
What's
water's
up?
moving tangentially.
Say that again?
The water has a tangential velocity.
The water has a tangential velocity. So it's an object that's got some velocity. Is there any reason that if you've got an object that's got velocity that it wants to change its velocity? No, it wants to keep going, right? So if there was a hole in the cup over here, then that water would just keep going, right? In a straight line. And probably wouldn't land on Brittany's nose, but might land on Brittany's toes, right? Does that make sense? It's going to go in a straight line, projectile motion. Oh, we can do that. We've done that before, right? So it's really, for the water, it's really the fact that the cup, kind of like Michael was saying before, is pushing back on it, right? Pushing it in, holding it in so that it can't go in a straight line. I saw a hand somewhere. Yeah?
I was just like, maybe the water's momentum keeps it in the cup long enough so that the force has already changed directions before it. Because, like, obviously if you held the cup at the top, it would fall out because the force is always changing the momentum to be able to keep it there.
So, yes, conceptually, but I would encourage you not to describe it quite that way.
Okay.
So, the reason that it doesn't fall is because it has velocity, right? And if it has velocity, it has momentum. So you can say that, but I wouldn't blame its momentum on the fact that it's not going anywhere, okay? Because it has velocity, it wants to continue in a straight line. The cup and the string are not allowing it to go in a straight line. Does that make sense? So it's preventing it from continuing in a straight line and keeping it in the circle. Is that okay? Okay. I want to make sure that I didn't miss anything from that before we move on. Okay, we're going to try a couple of problems, a ranking test, and a couple of little things before it's time to go. Does that sound okay today? All right. So here we go. I'm going to make this a little bit smaller so you can see the whole thing. Here's the situation. You've got a car traveling clockwise at a constant speed around an oval track. It says in the table below, indicate the direction of the velocity and acceleration of the car at each of the labeled points, R, S, T, U, V, and W. Use the direction labels over here in this little rosette thing, okay? If you believe that there's no vector or no direction, use the letter J. If you think it's going into the page, then use K. Out of the page is L. If nothing is right, then tell me M. Okay? I'm going to give you a moment to work on this by yourself, and then I'll let you guys discuss. Does that sound okay? All right. Take a look. There are lots of questions here, so it'll take a minute. And I'm going to start with you. Does that sound okay? Can you tell me the velocity for at point R? She says C. What do you guys think? Do you agree with her?
Yeah.
Awesome. All right. Jack, what did you guys say for the acceleration at R? D? No? Oh, changing stories? What did...
We had M.
M. Do you agree with that?
No.
They're just... Maybe they're just going to disagree. You could like just start saying all the letters of the alphabet. What are you guys upset about? What did you say, Alex?
We said D.
You said D. Do you guys agree with that?
Yes.
There are some yeses. Brittany is just obstinate. What did you say?
We said J.
They said J.
They're over in the directions.
Where?
In the directions.
I see.
In the
J
instructions?
for no direction.
Oh,
K
I
for
see that.
intermediate.
I'm like, where is it?
Okay. Was there anybody that had something other than M, D, or J? Oh, Michael, what did you guys have? E. Okay, we've got some decision making to happen here. What do you think? Lindy?
It's moving in a constant velocity or constant speed. We know that. So
Okay.
it's not changing direction, and so it's not accelerating. So it's J.
So it's moving with a velocity in that direction, not changing direction, which means that the acceleration has to be what?
0.
No direction, that's just zero.
Oh, okay. So I guess we want N. 'Cause no direction means it's still.
I took it as J,
Okay.
personally. I that's what I had written down. But I could say either M or J. I think that they're kind of, I mean, to me, M means that there is another answer that is correct. Yeah. So I'll say M or J. Is that okay with everybody? Okay. So let's do M or J. All right, Keegan, what did you guys say for the velocity for S?
D.
D. What do you guys think? Do you agree with him? Anybody want to fight about that one? Okay. And Michelle, what did you guys say for the acceleration for S?
F.
F? Do we agree?
Yes.
Yeah? Cool. And the game here, friends, is that if we look at this, the direction of the velocity for S and the direction for the acceleration for S are going to be what? They will always be perpendicular. This might be something to write down. In uniform circular motion, the velocity vector and the acceleration vector will always be perpendicular. It should make sense because the velocity is going to be tangent to the circle or perpendicular to the radius, and the acceleration will always be in the direction of the radius. So if you got one that's always got to be perpendicular and one that's always got to be parallel, then they've always got to be mutually perpendicular to one another. Is that okay? All right. Cameron, what did you guys say for the velocity vector for T?
E.
It says E. What do you guys think? Do you agree with her? Excellent. And what did you guys say for the acceleration vector for T? G. We doing okay? Okay, we're going to double time this now. So, Peter, what did you guys say for velocity and acceleration at U?
G and M/J.
G and M/J. Do you guys agree with that?
Yeah.
Okay, I like that we've decided to, compromise there. And Amanda, what did you guys say for V?
H and then B.
H and B. What do we think? Is that okay? All right. And Lindy, what did you guys say for W?
A and C.
A and C. We agree with that?
I guess.
Yeah? Okay. Making sense? Direction? Let's plug in some numbers to this and make sure this is okay too. So, here's the next situation. We got a 150-gram ball at the end of a string revolving uniformly in a horizontal circle. So we can imagine this is like the yo-yo on the floor, right? Swinging it around. Uniform circular motion, horizontal circle with a radius of 0.6 meters. Says that the ball makes 2 revolutions every second. So you're going to have to use a little bit of those skills from last chapter, okay, to get some conversions done. The question is, what is the centripetal acceleration? I'll let you work on that for a minute. You are welcome to talk to your partners. I think that would be a...
meters for rotation, and then 2 rotations per second. Yeah. So omega is 4 pi, right? And then velocity is omega to 10 pi. That's and then you get times to get you have to get rid of velocity.
Yeah, sure, you take some of
Yeah, take it times radius, but then you have to divide by 2 pi to get rid of radius. Yeah.
How is V related to omega?
And then divide radius. That way.
You multiply like by the radius.
Yeah. So you could certainly do that. Are we doing okay so far? So the radius is 0.6. I think a lot of people wanted to go this way. You didn't actually have to do this. You can do it straight from tangential stuff, but I think that this seems the most natural now that we know how to do it. Seems to make pretty decent sense. And then V is omega times R, so that's going to be 7.54. And then from there you can find the acceleration, right? Centripetal acceleration is just going to be V squared over R. What are we getting for a value?
94.7.
It's a lot, right? 94 point, what'd you say? 7.5. Goodness. So like 94.8, can I say that?
Yeah.
What are the units?
Meters per second squared.
It's true. And if this ball is sitting on the floor and going in this circle, can you tell me what the tension in the string is? How would you do that? Well, let's take a look, right? So if we draw the free body diagram, the only thing that's really pulling it in is tension, right? So we'd say that F net, write this down before you go, I'm almost there, oh my goodness, F net in that tangential plane is just going to be equal to the tension, and F net also equals what? Mass times acceleration. That's all we're doing. We've just got an acceleration that happens to be centripetal, so you're going to plug that in. So take that take the mass of, so it's going to be 0.15 kilograms. Multiply that by the 94.8 or whatever it was. And that's not a hard question. 14 point what?
22.
Units are? Newtons. All right. My friends, we have made it. It is spring break time. I hope that you have a really, really wonderful week.